Okay, so in this lecture, we're gonna discuss about conjugacy, conjugacy in the symmetric group Sn. Okay, a quick, recall I'll do of what a conjugacy class is. Okay, so conjugacy class. Okay, so if you remember what I think you should have a prior knowledge of what action of a group on itself is by conjugacy. I'll give the reference to the video of mine in the I button. So, so basically what we have is we have a group G. We make G act on itself by conjugation. That is such that an element G acts on the element A by the operation G inverse. Okay. So this is called the action of a group on itself by conjugation. So this happens for all G in G and for all A in G. Clear? Okay. So if you have two elements, say you have two elements A and B in G, then A and B are said to be conjugates if there exists an element from the group denoted as small g such that A is G, B, G inverse. So that's the definition of two elements being conjugates. Okay. Now let G be acting on itself. Then what we do is we consider the set, say, let us denote it as box A, which consists of the elements which are conjugates to A. So it consists of the elements of the form G, A, G inverse, such that small g in capital G. Then the small a is called the, wait a sec, yeah, so this small a is called the conjugacy class of A, is the conjugacy class of small a, which is an element from G. Clear? Okay. So let us now start with what conjugacy in Sn looks like. Okay. That is the topic of this lecture. So let us start. Okay. So yeah. So the first thing which we will be discussing is a proposition. What is this proposition? So we say that let us consider two elements from Sn. So let sigma and tau be two elements from Sn, and suppose sigma has a order decomposition, has a cycle decomposition. So it's a cycle decomposition. So the cycle decomposition is of this form. Let's say A1, A2 till some AK1, then you have B1, B2 till some BK2, and so on. C1, C2 till some CK3, and so on. Okay. Then tau sigma tau inverse has the cycle decomposition. So it's of the form tau A1, tau A2 till tau of AK1, then you have tau B1, tau B2 till tau of BK2 and so on. So if you don't know what cycle decomposition is and what these notations actually mean, so I'll give the reference to the video on symmetric groups in the I button. So let us prove this. The proof is pretty quick. Yeah. So basically observe that. So if sigma sends I to j, then what does tau sigma tau inverse of tau I is? Okay. Then tau sigma tau inverse of tau I is nothing but tau j, right? Therefore, if I, j, two elements appear as ordered pair, as an ordered pair in a cycle decomposition, or I should reframe the sentence as, because since we are talking about a cycle decomposition, I should not mention an ordered pair inside it. So if the ordered pair Ij appears in the cycle decomposition of sigma, then tau I tau j will obviously be in it, right? Then tau I tau j appears as well. Appears as well in the cycle decomposition of tau sigma tau inverse. Clear? And that is pretty quick from this fact. Clear? Because if I and j appear in the cycle decomposition of sigma, so that typically means that sigma sends I to j, right? And we know that if sigma I sends tau to j, if sigma sends I to j, then tau sigma tau inverse sends tau I to tau j, right? Therefore, if ij appears in the cycle decomposition of sigma, and that happens because I is sent to j by sigma, since tau I is sent to tau j by tau sigma tau inverse, so tau I and tau j as ordered pairs appear in the cycle decomposition of tau sigma tau inverse as well, right? Okay. Okay, let us take a quick example of this. So example of this, let's say, suppose we have sigma equals to 1, 2, 3, 4, 5, 6, 7, 8, 9, and tau equals to, let's say, 1, 3, 5, 7, 2, 4, 6, 8. Then you can obviously calculate what tau sigma tau inverse is, and that comes out to be 3, 4, 5, 6, 7, and 8, 1, 2. So you can obviously observe that the length of the cycles are correspondingly similar, right? Clear? Okay. And that was the exact proposition. So actually this proposition leads us to the fact that what's the concept of cycle types? Okay. Sorry. So definition. If sigma is an element of Sn such that it is the product of disjoint cycles of length n1 n2 till say some nk, with the length of the cycles are in increasing order, including the one cycles. Okay, obviously we will include the one cycles in this case, including one cycles. Then the integer n1, n2 till nk are called the cycle types. The cycle types of sigma. So in this case, we have the cycle type as 2, 3, 3. Right? Clear? So, furthermore, if n is a positive integer, then a partition of n is any non-decreasing sequence of positive integers, whose sum is n. Okay. So I guess the concept of partition is pretty well known because that's quite used. But for a simple example, if you consider the number 3, then 3 can be written as 3, it can be written as 2 plus 1, and it can be written as 1 plus 1 plus 1. So these are the three possible partitions. For example, if you have the number 5, it can be written as 5, it can be written as 4 plus 1, it can be written as 3 plus 2, 3 plus 1 plus 1, you can write it as 2 plus 2 plus 1, then 2 plus 1 plus 1 plus 1, and 1 plus 1 plus 1 plus 1 plus 1. Yeah. Okay. So these are the possible partitions, right? Okay. So this leads us to the next important proposition. The proposition is as follows. So if you have two elements in Sn, then the elements are conjugates if and only if they are of the same cycle type. They are of the same cycle type. Okay. The number of conjugacy classes of Sn equals the number of partitions of it. The number of partitions. Okay, so let's check this. Okay. Now obviously we have simply proved the necessary condition of the first statement, right? That if two elements are conjugate, then they are having the same cycle type, right? So that is what we proved at the starting of this lecture. That if you have if you have a permutation sigma from Sn which has the following cycle type, then tau sigma tau inverse has the same cycle type. So conjugates have the same cycle type. That's already proven. So in this, so the only thing which we actually need to prove here is that if two permutations have same cycle type, then they are conjugates. Okay. So let's start with it. Okay. You can also obviously start up with an example of this form, which will help us in constructing how. So this proof is quite constructive. Okay, and the construction relies on observing a very specific example. So let us start with an example first. Okay. So an example. So suppose you have permutation sigma 1 which has the cycle type of 1, 3, 5, 8, 9 and 2, 4, 7, 6. Clear? And sigma 2 has the cycle type, let's say 3, 4, 7, 8, 1 and 5, 2, 6, 9. So it's utterly obvious that sigma 1 and sigma 2 has the same cycle type. Now, if I list these elements like this, so sigma 1 has the elements listed as, so 1 here, 3, 5, 8, 9, 2, 4, 7 and 6. Okay. And sigma 2, we have the corresponding elements as 3, then we have 4, 7, 8, 1, 5, 2, 6, 9. Okay. What we do is we map each corresponding element. So we map 1 to 3, 3 to 4, 5 to 7, 8 to 8, 9 to 1, 2 to 5, 4 to 2, 7 to 6 and 6 to 9, and tau is defined as this very mapping. So if you carefully notice what tau is, then tau is this mapping. Let me change the color. So tau is this mapping. So it's, so 1 goes to 3, 3 goes to 4, 4 goes to 2, 2 goes to 5, 5 goes to 7, 7 goes to 6, 6 goes to 9, 9 goes to 1. So you're only left with 8. Yeah. So this is the this is what tau is basically, right? Now if you find what is tau sigma 1 tau inverse, then it will come out to be sigma 2. It will come out to be sigma 2. Clear? Got it? Now there can be multiple such elements, multiple such permutations tau. Because if we reorder the elements in sigma 2 as, suppose sigma 2 is reordered as, let's say sigma 2 is reordered as 3, 8, 1, 4, 7, 5, 2, 6, 9, then we have to map. So if I consider this listing only, so I will have to map 1 to 3, 3 to 8. Okay, let me just list them again. Okay, that will give a better visualization. So I'll just so I had sigma 1 as, so the list elements listed were as 1, 3, 5, 8, 9. Then you had 2, 4, 7, 6, right? 2, 4, 7 and 6. So here you have 8, 3, 8, 1, 4, 7, 5, 2, 6 and 9. So actually again we do the same procedure, that we map the corresponding elements. So we map 1 to 3, 3 to 8, 5 to 1, 8 to 4, 9 to 7, 2 to 5, 4 to 2, 7 to 6 and 6 to 9. So what does tau come out to be? So 1 goes to 3, right? 1 goes to 3, 3 goes to 8, 8 goes to 4, 4 goes to 2, 2 goes to 5, 5 comes back to 1. What are the elements left with? So we have, yeah, 6 goes to 9, 9 goes to 7, 7 comes back to 6. Yeah, so this is tau. And obviously we are obviously obeying the same procedure. So tau sigma 1 tau inverse is again sigma 2. Right. So therefore there is no discussion about the uniqueness of such a tau, such a permutation tau. So the proof completely relies on the fact that such a tau exists, and that is pretty obvious from the procedure we followed, right? So we can obviously come up with a constructive proof of what we just did. Okay. So the proof is like, we can say it like this, that suppose sigma 1 and sigma 2 have the same cycle type. Okay. Now we order these cycles in a non-decreasing length, including the 1 cycles, which is pretty trivial from the definition of cycle types, right? So we order these cycles in non-decreasing way, including the 1 cycles. Clear? No 1 cycles. Ignoring the parenthesis, each cycle decomposition is a list in which all the integers from 1 to n appears at least one, right? So ignoring the parenthesis, each cycle decomposition, so it's a list of all integers from 1 to n appearing exactly once, right? Appearing exactly once. Yeah, so each cycle decomposition including the 1 cycles. Right? So appearing exactly once. So what we do is we define tau to be the mapping which maps the ith integer in the list of sigma 1 to the ith integer in the list of sigma 2. Okay, then tau is the permutation, then tau sigma 1 tau inverse will be equal to sigma 2, then and since the parenthesis which delineate the cycle decomposition appear in each list, we have the required result. Clear? So I should remove the word and here because this happens, since this happens, yeah, we have the required result, that is which implies sigma 1 and sigma 2 are conjugates. Clear? Okay. Now since there exists a bijection between conjugacy classes of Sn and the permissible cycle types, okay, so let me just write it in words. Since there exists a bijection between the conjugacy classes of Sn and the permissible cycle types, and each cycle type is a partition of it, right? And so each cycle type is a partition of n. That is pretty obvious because the cycle type, the maximum length of the cycle type can be n, and if you have multiple cycles, then the summation of the length of each of the cycles must equal n, and the cycle types are arranged in non-decreasing order, so that obviously forms a partition of it, right? And each cycle type is a partition of n, hence the second proposition is proved. right? So let me go through a quick example. So observe, suppose you consider S5. Okay. So what are the conjugacy classes of S5? Okay. So let's come up with that. So what are the possible partitions of S5? And what are the conjugacy class representatives? Conjugacy class representatives. That is, you can think of them as, what is the element whose conjugacy class which we are considering. Okay. That is, the conjugacy class was defined as block A, right? So what is this element A? That is what we are talking about. So the possible partitions are of the form 5 ones, 3 ones and 1 2, 1 1 3, 1 4, 5, and I have 2 1 2 2 and 2 3, right? So the first thing which we actually do is that we find LCM of these elements in the partition. So the LCM of the first one is 1. So the conjugacy class representative of that is 1. Here we have the LCM as 2, so the representative is a cycle of order 2. Here we have 3, so it's a cycle of order 3. Here it's 4, it's a cycle of order 4. And it's 5, so it's a cycle of order 5. Here you have again the LCM to be 2, but you have 2 2s, right? So you have 2 2s. So it is of the form 1 2 and 3 4. And you have 1 2 and 1 3, right? 1 2 and 1 3. So we have a 2 cycle 1 2, and we have a 3 cycle 3 4 5. Okay. Yeah. That's what we actually do. So what we do is we find out the maximum number of the partition we have. We consider that cycle. In the first cases, you can consider like that, and or you can just ignore the 1 cycles and just find the cycles of the other lengths possible, right? So you have a 2 cycle here, 2 3 cycle here, 4 cycle here, 5 cycle here, 2 2 cycles here, and 1 2 cycle and 1 3 cycle, right? Now some trivial observations about this, if I say, then think of it like this. Suppose sigma is an M cycle in Sn, then what are the number of conjugates? Then the number of conjugates. So the number of conjugates is of the form n into n minus 1 till n minus m plus 1 by n, right? Right? So it's pretty obvious from the fact. Then what is the index of the centralizer of sigma? Then index of the centralizer of sigma is, which is Sn by this, so it's A, right? It's A. Exactly, this is the number of conjugates, right? Right. Now, so number of elements in Sn is n factorial. This implies number of elements in this is, so it goes here, yeah. So it's n factorial divided by this. So it's n factorial times n minus n factorial. Okay. I guess it's pretty clear. So yeah. So what is the immediate conclusion which you can draw from here is that, so if sigma is an M cycle in Sn, then the centralizer of sigma in Sn is defined as the set of elements of the form sigma I times tau, such that I is between 0 and m minus 1, including the both. and tau is an element from Sn minus m. So this is an immediate result from here, right? That its order is of this form. Clear? What is Sn minus m? So Sn minus m is a subgroup of Sn such that elements in Sn minus m it fixes all elements in the m cycle. Fixes all elements in the m cycle outside these n minus m elements. That's pretty obvious to notice, right? Right. For example, if you have sigma equals to say 135 in S7, then the centralizer of sigma are elements of the form 135 to the power I times tau, such that I ranges from, or I is equals to, so what is m here? So m is here, so what was m here? Right? So sigma is an m cycle, right? Sigma is an m cycle. So here sigma is a 3 cycle. So I can take the values 1, 0, 1 and 2, right? And tau must be in S7 minus 3, right? So it's of the form S4, right? Where tau fixes, since tau is an element from S4, or I should rather not write it as S4, I should write it as S7 minus 3. Tau fixes this m cycle, right? So tau fixes 1, 3 and 5. Okay, so this is all about conjugacy in Sn. I'll try to give a reference to the playlist I have about group theory, where I have discussed certain prerequisites and certain topics related to this lecture, which will be quite helpful, I think. So meet you guys in the next lecture.